Hello, and this is the 11th module of the course on econometric modeling. So far we have introduced the course, that is in terms of what is econometrics, and after that we got into simple regression analysis. So, where we had only two variables. Now, we are getting into multiple regression analysis, that is when we will be having more than two variables, or there will be more than one independent variable. So, when we say that there were only two variables, one is independent variable, another was dependent variable. Along with that, there was a constant term. Now, constant terms are always there unless and until there is a special situation or case, but now when we talk about multiple regression analysis, then it basically involves one dependent variable, but several independent variables. So, it can be two or more. So, that is how we have three modules on the basic of multiple regression analysis. So, the first module on multiple regression analysis. Multiple regression analysis is just a generalization of simple linear regression with one independent variable to two or more independent variables. So, we move from one independent variable in the case of simple linear regression to two or more independent variables. Thus, a multiple regression model with k plus 1 independent variables can be written in the population as y equals beta naught plus beta 1 x 1 plus beta 2 x 2 plus beta k x k plus u, right. Now, we have mentioned here k plus 1 because 1 here refers to the constant term, and this k can take any value which is 2 or more, right. So, in case k is 1, we have the simple regression case. When we have k equals to 2 or greater than 2, then we have the multiple regression case. So, where beta naught is the intercept which we were earlier denoting by alpha. So, beta naught is equivalent to our previous alpha, and beta j equals 1 to k are the parameters associated with the independent variables, and u is the error term, the usual error term. So, we can write the multiple regression model in matrix form. That actually saves us a lot of computation, and it is much more convenient to deal with multiple regression in matrix form. So, the equation 1, which was this equation 1, can be rewritten more compactly in matrix forms such as y equals x beta plus u, where this is my y. So, y is a vector of observations on the dependent variable. We are now dealing with, say, cross section data. So, we have n observations, right, and consequently the dimension of y will be n by 1. So, there are n rows and only one vector. I have also mentioned here the dimensions of the matrices and vectors of the variables and parameters, and so accordingly you can see that x, the matrix of independent variables, will be having n rows and k plus 1 columns. So, this is the one column and these are the k columns for the k independent variables. So, we have k plus 1 columns, and beta is again a vector which is of the dimension k plus 1 multiplied by 1. So, there are k plus 1 rows and only one vector, and u, the error terms, has a dimension of n by 1. So, there are n observations corresponding to that there is only one column. So, you can see that we multiply x with beta. So, multiplying x with beta, we have n by k plus 1 multiplied by k plus 1 by 1. So, x beta gives us a vector of n by 1, y is n by 1 and u is anyway n by 1, right. So, the equality has been established, and accordingly we can always write this model as y 1 equals x 1 beta plus u 1, right. So, this x1 actually corresponds to the observations on k independent variables related to the first unit, that is, this is the first observation or first entity from which we are collecting data, and this actually corresponds to the observations from the first entity on k variables. And then we have of course the k parameter estimates or k parameters in the population, and there will be one error term u1, and similarly we can have y I equals x I beta plus u I and so on. So, in case of now if we try to draw analogy between this k plus 1 variable case and 2 variables case, that is when k is equal to 2, or rather here k is equal to 1, but in totality we have only 2 variables. So, in that case I have one independent variable, the vectors of parameters are beta naught beta 1, which is actually our original alpha and beta, and then we have a vector of the error terms. Previously the residual sum of squares or RSS was minimized with respect to alpha and beta. In the multiple regression context, in order to obtain estimates of the parameters, that is beta naught beta 1 to beta k, the residual sum of square would be minimized with respect to all the elements of beta. Earlier it was only 2 variable case, now we would be arriving or trying to derive the fitted regression line by choosing the all the values of the parameters beta naught to beta k. We minimize the residual sum of square by choosing the parameter values of beta naught to beta k. Now, the residuals can be stacked in a vector, which is very similar to the population error. The way population error has been stacked, the residuals can also be stacked, because we minimize the residuals, not the population variance or the population error. So, we need to bring in the concept of residuals, and this is so because we work with a sample, we do not work with the population most often, and that is why we minimize the residuals and not the population error actually. So, here in this case our Lagrange is set as, so Lagrange multiplier, or basically the expression by minimizing which we are obtaining the values of the parameter estimates. Here in this case is u hat prime u hat. You can see that u hat prime u hat was a n by 1 matrix. So, u hat prime, which is the transpose of u hat, is actually a 1 by n vector. So, this is 1 by n, this is n by 1, 1 by n by 1, I have a 1 by 1 number. So, this is actually a number which is u hat n square and summed over all n observations. Alternatively, since u hat is equals to y minus x beta hat, what we are minimizing is u hat prime u hat with respect to beta hat, and this is the expression because u hat is y minus x beta hat. You know that y equals x beta plus u, its sample counterpart would be y equals x beta hat plus u hat. So, y minus x beta hat is equals to u hat. So, this is y minus x beta hat prime corresponding to u hat prime, and this is y minus x beta hat. And when I expand it, then I will be having y prime y. So, y prime y, then x prime beta hat transpose is beta hat transpose x transpose. So, beta hat transpose x transpose multiplied by y. Similarly, I have y prime x beta hat and then again beta hat prime x beta hat. Note that this is a 1 by 1, this is of 1 by 1 dimension, which implies that this is also a number. Since u hat prime u hat is a number, the left hand side is a number. So, the right hand side also has to be a number, fair enough. So, we are now going to minimize this expression. So, first of all what we are going to do is that, or explaining, we would be taking derivative of this expression with respect to all the betas. So, since there are k plus 1 betas, we will be arriving at k plus 1 linear equations in k plus 1 unknowns, and these unknowns are beta naught hat, beta 1 hat and so on up to beta k hat, and these are the equations that we arrive at or obtain when we take the first derivative of this expression with respect to individual betas. These are called the OLS first order conditions, very similar to the OLS first order conditions that we had obtained in case of simple regression. There we had only 2 first order conditions, now here we will be having k plus 1 first order conditions. Now solving for the first order conditions, the k plus 1 parameter estimates are beta hat is equal to x prime x inverse x prime y. So, this is a very crucial derivation where we say that beta hat is x prime x inverse x prime y. This is a k by 1 vector. So, this also has to be k plus this is k plus 1 by 1. So, this also has to be a k plus 1 by 1 vector. Okay. So, once we have this expression, then equating each row with the corresponding row, we can have values of betas, that is starting from beta naught hat to beta k hat. Now, we get into actually the derivation of this thing. So, how do we arrive at x prime x inverse x prime y? Now, if you remember in the previous slide, we had this expression minimizing u hat prime u hat is equal to minimizing this expression. These are of dimension 1 by 1. So, by taking the first derivative with respect to beta hat, where this is actually the true operation, I am taking the first derivative of u prime hat or u hat prime u hat with respect to beta hat individual betas, and that is how we have this expression, right. Now, by doing so, we will be arriving at this expression. Why this is so? Because you see that since this is a 1 by 1 dimension, individual components are also 1 by 1. So, they are all numbers, right. Now, when we take the first derivative of y prime y with respect to beta hat, this is 0 because beta hat does not exist here, and these two can be written as minus 2 beta hat prime x prime y, or it can also it could have been also written as minus 2 y prime x beta hat. Now, when I take the derivative with respect to beta hat, then I will be arriving at minus 2 x prime y, which is this expression or this part, and this is actually equivalent to obtaining a plus 2 beta hat x prime x, right. Now, from this two thing we can always, so this is the expression minus 2 x prime y plus 2 x prime x beta hat, and then from here this is set equal to 0 because this is first order condition, and then from here we arrive at the expression for beta, which is x prime x inverse x prime y, right. X prime x is actually ahead of beta hat. So, when I take this to the other side, this becomes 2 cancels out. So, I have x prime x beta hat equals x prime y, which implies beta hat equals x prime x inverse x prime y. So, this is the expression we arrive at. Now, we talk about the assumptions of multiple linear regression. They are exactly the same as that of simple regression. So, first of all, the model in the population can be written as y equals beta naught plus beta 1 x plus beta 2 x and so on plus u, where the betas are the unknown parameters of interest and u is the unobservable random error term. So, the first assumption relates to the model specification in the population. Second, we have a random sample of n observations. So, x I1, x I2, x ik and y I running from 1 to n following the population model. So, the second assumption states that we pick up a sample of size n observation from the population. The third assumption states that there is no perfect collinearity. In the sample, there are no exact linear relationships among the independent variables. This allows the independent variables to be correlated, but they cannot be perfectly correlated. Perfect collinearity might happen when two independent variables are multiples of one another. So, this is an assumption which we will be dealing with in the next part when we talk about the problem of multicollinearity. For the time being, this simply assumes that there cannot be perfect collinearity among the independent variables, which essentially implies that one variable lies completely in the column space of other variable, or maybe one variable is 100% or fully explained by the other variable. So, for example, in case of independent variables, suppose I have one independent variable age. So, I jot down the age of individual respondents, and if I have another variable which is 3 multiplied by age. So, this is a case of perfect collinearity, because you can see that this independent variable is completely it lies completely in the column space of this independent variable or vice versa. So, we cannot have perfect collinearity among the independent variables. This is the basic idea, and what are the problems arise and why can't we have it, that will be discussed at length when we discuss the problem of multicollinearity. So, continuing with the assumptions, the fourth assumption is that the error u has an expected value of 0 given any values of the independent variables, that is expected value of u conditional upon x is actually equal to 0. This is also an assumption we have dealt with at length while discussing the assumptions of simple regression analysis. So, for example, consumption and income functions are related as consumption equals beta naught plus beta 1 income plus beta 2 income square plus u. So, if income square is not included in the specification, then this assumption would be violated. So, you can see that u is not only, this assumption states that u is not only independent of the observation x, but it is also independent of any functional form of x. This has been repeated earlier. So, under this assumption, we often say that x are exogenous explanatory variables. So, when this assumption is fulfilled, then x's are called exogenous. If x j is correlated with u, then x j is said to be an endogenous explanatory variable. So, first of all, the entire matrix X, that is all the independent variables, need to be exogenous. If any one of them is not exogenous, then we call it an endogenous variable. And then we arrive at the last assumption, the fifth assumption, the assumption of sphericality. But before that, we talk a little more about the previous assumption. For a sample, this assumption implies that the residue is uncorrelated with the regressor, that is x prime u hat is equals to 0. This can be also proved very easily, that x prime u hat is actually x prime y minus x beta hat, which is, if I now expand, x prime y minus x prime x, this is x prime x, and then this is the expression for beta hat, x prime x inverse x prime y. This is the expression of beta hat. So, we have x prime x from here and x prime x inverse x prime y. Now, you can see that x prime x and x prime x inverse, they cancel out, and I have x prime y minus x prime y, which also cancels out, and we have 0. So, if beta hat has this formula, then we can prove that x prime and u hat, they are independent of each other or uncorrelated with each other. So, this actually follows also implies that the independent variables are exogenous, that is, they are not correlated with the error term. Now, talking about the last assumption of sphericality, this actually houses two assumptions. The first assumption is of homoscedasticity, that is, the error u has the same variance given any values of the explanatory variables. So, variance of u given x1 to xk is equal to sigma square. This assumption also encompasses another factor or another assumption, and that is there is no correlation between the error terms. So, covariance between u I u j is equal to 0. This is covariance between ui and uj is equals to 0. This is another assumption. So, we do not assume any correlation among or between the error terms, and we also assume a constant error variance, that is variance of u equals sigma square. Now, this is written as expected value of u prime conditional upon the values of x equals sigma square I n, where I n is an nth order identity matrix of order n by n, and the implications have already been mentioned. Now, I expand this expression specifically expected value of u prime given x and how we arrive at the value or the expression sigma square I n under these assumptions. So, the assumption of sphericality if expanded, first of all I have u prime, you know that u is an n by 1 matrix, u prime will be a 1 by n matrix. So, u prime conditional upon x is an n by n matrix. So, this is an n by n matrix, right. So, first of all I expand them, then I multiply, and the expected operator is brought inside. So, we have expected value of u1 square given x, then u1 u2 expected value of u1 u2 given x, and so on. Now, since any two ui's are uncorrelated, expected value of ui uj given x is 0, right. This is called the assumption of no autocorrelation. So, all this u2 un, u1 un, un u2, u2 u1 and so on, all of them are equal to 0. And the second thing, that expected value of ui square conditional upon x is sigma square for all I. This actually makes these expressions equal to sigma square. So, the diagonal terms are all sigma square. Sigma is independent of the observation. So, sigma is just a constant number, it is not dependent on the ith observation or jth observation. So, we have sigma square along the diagonal terms, as a result of which finally we have sigma square multiplied by I n, where I n is an n by n identity matrix. Fair enough. So, this is how we present the assumption of sphericality, which encompasses two assumptions of homoscedasticity and no autocorrelation among the error terms. Now, talking about the properties of estimated parameters, beta hat, the OLS estimators are unbiased estimators of the population parameters. So, we again stick to the concept of LU, best linear unbiased estimators. Alternatively, expected value of beta j hat is equals to beta j for any j 0 to k. Now, we just prove it that expected value of beta hat is expected value of x prime x inverse x prime y conditional upon the values of x, right. Now, y can be expanded as x beta plus u. Now, getting into the multiplication or further expanding it, I will be having x prime x inverse x prime x beta. So, these two terms cancels out and I am only left with beta plus x prime x inverse x prime u, which actually remains here. So, x prime x inverse x prime u, and I take the expected value of u only because x prime x inverse x prime conditional upon x is non-random. So, we cannot have any expected value operating on that expression. So, expected value of u given x is 0, as a result of which expected value of beta hat is equal to beta. And now, since beta is a vector consisting of all the terms like beta naught hat, beta 1 hat and so on, where beta naught hat is the constant term. So, we do not need any separate proof for individual beta parameters. This itself implies that all the estimated parameters are unbiased. Now, talking about the other property, that is the OLS estimators are best estimator or minimum variance estimator, or when we talk about the efficiency of OLS estimators, we use the Gauss-Markov theorem. Gauss-Markov theorem justifies the use of the OLS method rather than using a variety of competing estimators. The theorem states that under the assumptions 1 to 5, the assumptions that has just been mentioned, beta naught hat to beta k hat are the best linear unbiased estimators or blues of beta naught, beta 1 to beta k respectively. That is, they are the best linear unbiased estimators of the population parameters. Having defined linear and unbiased estimators, best implies that the estimators have the smallest variances. The theorem says that for any estimator, say beta j tilde, that is linear and unbiased. So, that has other properties of the OLS estimator, variance of beta j tilde will be greater than equal to variance of beta j hat, that is the OLS estimator, and the inequality is usually strict. So, we would often come across variance of beta j hat greater than variance of beta j variance of beta j tilde greater than variance of beta j hat. In other words, in the class of linear unbiased estimators, OLS has the smallest variance. Okay. So, now we derive the variance of OLS estimators. Variance of beta hat is a k by k matrix, where variance of beta hat would be written as beta hat minus beta multiplied by beta hat minus beta prime, and then instead of variance we have the expectation operator. Fair enough. Now, I multiply them and then this expression is arrived at simply. Okay. So, we have variance of beta hat. So, this expression, this matrix can be rewritten as variance of beta 1 hat, covariance between beta 1, beta 2, beta 1 hat, beta 2 hat, and so on. So, these are equivalents to variance of beta 1 hat, and this is equivalent to covariance of beta 1 hat, beta 2 hat, and similarly we can have other covariances and variances, right. Now, we get into an alternative procedure where we have just shown you that beta hat is equal to beta plus x prime x inverse x prime u, right, which implies that beta hat minus beta is x prime x inverse x prime u. So, now I just focus on this term and beta hat minus beta is replaced with x prime x inverse x prime u. Again beta hat minus beta prime is replaced with u prime x into x prime x inverse, right. And what happens? These are actually non-random entities. So, they are we do not have expectation operating on them. So, expectation actually is working only on u prime. We know that u prime, expected value of u prime is sigma square I n. So, sigma square being constant actually comes out, and what I am left with is x prime x inverse x prime I n x x prime x inverse. So, x prime I x is actually x prime x because I is an identity matrix. So, these two things cancel out and I am left with sigma square x prime x inverse, which is the variance of beta hat. Now, I mean we actually, if you remember, while working with simple regression analysis, I did not derive the variance of alpha hat, I only derived the variance of beta hat, and I mentioned that derivation of variances are easier when we work with matrix algebra. So, in case of k variable case, that is 2 variable case, that when k is equal to 2, then we have this matrix and our beta hat is actually beta naught hat beta 1 hat, which is equivalent to our alpha hat beta hat with the simple regression case. So, x prime x is this is x prime x, the determinant of x prime x. So, once I obtain the determinant of x prime x and denote it by a, I arrive at x prime x inverse as this expression for the 2 variable case, right. Okay. So, this is my x prime x inverse. Now, you remember that beta hat, the variance of beta hat is sigma square x prime x inverse. Okay. So, I have sigma square here, right, and what does this give me? This gives me the variance of beta naught hat, this gives me variance of beta 1 hat. This is equivalent to covariance between beta naught hat and beta 1 hat, and this is equivalent to again covariance between beta naught hat and beta 1 hat. You can see they are the same terms. So, 2 are covariance between beta naught hat and beta 1 hat. This is variance of beta naught hat or alpha, and this is variance of beta 1 hat or variance of beta hat in case of simple regression. So, these are the expression for variance of beta naught hat, which can come directly from the expression of the matrix that we have just arrived or derived in the previous slide, and this is the variance of beta hat, or here in this case beta 1 hat. So, that brings me to some discussion on the multiple linear regression model, and these are the books which you can follow for further understanding. In the next also we will continue with the derivation of some important theorems will be discussed in the next module, along with the derivation of unbiased estimators of the residual or the population variance. So, we will be deriving the residual variance as an unbiased estimator of the population variance. Thank you.